Hey everyone, I'm Rob May. I'm the co-founder and CEO of Neurometric.
And I'm Cooper, COO here at Neurometric. We're co-founders, and this is Inference Time Tactics, a podcast for builders, researchers, and engineers who want to understand what's really happening in the next era of AI.
So we're building the inference optimization layer for AI, and that word inference is doing a lot of work because the next performance gains in AI are not just about model size or training data. They're about how we use reasoning and thinking algorithms at runtime.
For the first episode, we're keeping it in-house. Rob and I are going to talk about why inference time compute matters, what we've been learning from reading hundreds of research papers, and where Neurometric fits in.
So this podcast is going to get pretty technical and pretty tactical. We are going to talk about things like verifier chains and beam search, and also about bigger architectural shifts towards more open, composable inference infrastructure. We're going to break it down with the people that are building at the very edge of what is possible.
All right, so let's get into it. We've been talking a lot as a team about inference time compute, and the more we dig in, the more it feels like this isn't just some incremental technical layer. It's a new way of thinking about performance. So we can start there. What is inference time compute, and why is it suddenly such a big deal?
Well, I think the first time since this is our first podcast, we should explain to people that there's a lot of terms for this that are used interchangeably. So inference time scaling, test time compute, inference time compute, and a few more. We're probably going to use inference time compute mostly when we talk about it here. But if you hear some of those other terms slip in as we have different guests on or talk about different topics, they all kind of mean the same thing. And what they mean is there's sort of three parts to building an AI model or running an AI model, right? One is all the pre-training, all the stuff that you do to get lots of data, to get lots of compute, to train the model with more stuff to make it better. Then there's post-training. So the fine tuning you do where you give it some context so that it knows a little more about your specific business. And then there's the inference time compute, which is what we're talking about. And these are a series of algorithms that you can run at the time you ask it a specific question or a prompt or a workload to get a better answer out. So let me give you a very, very simple example. One of the most popular inference time compute algorithms is called best of n, just the letter n. And that simply means ask the same question 5 times. These models run with an underlying probability distribution. And sometimes the answer you get out is high probability, sometimes it's low probability. And that's why these models hallucinate, because sometimes you get the low probability answer out or something like that. Now, if you ask it the same question 5 times and you get the same 5 answers, the model has a pretty high confidence rate that this is the right answer. So that's a really, really slimmed down example of what inference time compute means.
So we're thinking about this as a programmable surface layer where we can improve performance dramatically. But why now? Why is this moment different from, say, 2 years ago?
We'll talk about this in a minute, but I actually went through and categorized a couple hundred research papers on this. And one of the interesting things about the whole inference time compute space is there was very little research done on it in 2022 and 2023. The research that was done was mostly focused on comparing it to the impact that inputs could have at training time, right? So you could do this thing at training time, do this thing at test time, or inference time, and what's the difference? Now, the thing that really set the world on fire was the September 2024 release of OpenAI's O1 model. It was the first reasoning model that did some really cool and impressive stuff. And we don't know exactly what they did in that model, but everybody suddenly jumped to try to figure out these different types of reasoning algorithms. We knew what some of them were from the academic literature, but you just started to see an explosion in interest in this space because the capabilities were so impressive.
So one takeaway I remember in some of the research is that sometimes inference time compute doesn't work really well. Sometimes it's even counterproductive. Our engineers are even seeing that in some of our tests. Can you unpack that a bit?
Yeah, so for those of you listening who aren't familiar with Neurometric, one of the things that we do is we build a sort of inference time compute optimization engine. So you can think about it as we optimize your reasoning algorithms that you run on top of your large language models. And the reason that you need that optimization is because, to Cooper's point, when I was reading through all these papers, one of the things that you see, and one of the things we've seen in some of our own research, is sometimes it doesn't move the needle at all. You can put a chain of thought algorithm, a chain of thought pipeline, or a best event algorithm, or tree of thought, graph of thought, beam search, all these different things, and you get out about the same thing you would get out if you ask the model a question without any of those things in front of it, or you get very marginal improvement. On the flip side, sometimes you see really, really dramatic gains. I mean, one of the most popular papers out there looked at a 1 billion parameter model that, with some inference time compute algorithms on it, performed as well as, or sometimes beat, a 405 billion parameter model. And those are, probably an order of magnitude almost difference in price to run. So those are pretty significant. But I do think, with all the growth that you're seeing in the space and all the new algorithms, I think you're going to see a lot more. Well, let me put it this way. Sometimes I think the reason it doesn't work is because it's just the algorithm is not right for that approach, for that question, for that data set, underlying data distribution. And I think as we get smarter about this space, because it's very largely unexplored, I think we will be able to find inference time compute gains on almost any kind of inference input.
And gains really matter. Like when we think about reliability and performance, and why many people are saying generative AI is overblown, right, in its promises. It kind of makes me think about the 3 nines thesis that you wrote about recently. Do you want to talk about that?
Yeah. So when you look at other types of software, particularly cloud computing software, there's this idea of how many nines of uptime does it have? And 3 nines means 99.9%. And so 5 nines would be 99.999%. And the difference there is, and so that's the percentage of the time that it's up and doesn't go down, because it's very difficult to design a system that will never, ever go down and have 100% uptime. And so the question is, how much downtime can your application take? And so I don't know exactly what they stand for off the top of my head. You could do the calculation, but 3 nines probably means minutes to a couple of hours per year of downtime. And then you get out to 6 or 7 or 9s or something like that, and you're talking about very, very little downtime. Seconds, tens of seconds per year. So and so those are typically codified in what we call an SLA, a service level agreement. So you buy a software and it says this has 5 nines of uptime, and they will credit you back some money if they don't meet that standard. So let's extrapolate that to this agentic world that everybody's talking about, right? We're building all these agents, and sometimes you have a large language model that is, say, 95% accurate on the average agent task. Well, the problem with that is when these agents do multi-step workflows, you have to multiply those probabilities. And so you have, for 95%, you have 0.95 times, if it's 5 steps, 0.95 times 0.95 times 0.95, 5 times. And when you start to do that, you start to get much lower numbers. So at 4, 5, 6, 7 steps, you start going down into 80, 70, 60 something percent accuracy across the whole workflow. So suddenly, the longer the workflow, the less accurate it is, which is problematic. And so that's going to kill a lot of like think about if you have an agent that does travel booking for you, and there's 7 or 8 decisions you have to make for every trip, and the agent's wrong 1/3 of the time because of these compounding errors. Like, that's not a very good experience, and that's going to cause people to not adopt that agent as a use case, right? So the way to get around that, I think, is you have to think about the sort of 3 nines or 4 nines or 5 nines of success rates for these agents, because if you take 99.999% accuracy per step and you compound that over like 5 or 6 steps, you still have a pretty high success rate. I don't know exactly what it is off my head, but we'll multiply it out here. We'll put it in the show notes. So how do you get there? And this inference time compute stuff, this stuff that's less than a year old still today, as we're recording this podcast, is really less than a year old of being out in the zeitgeist and really adopted by lots of places. That's what's going to make the difference, because we're just not seeing the gains on the model side with additional training that we used to see. The jump from GPT-3 to GPT-4 was pretty big. The jump from GPT-2 to GPT-3 was pretty big. The jump from GPT-4 to GPT-4.5 was described by most people as disappointing. and I think they expected more. And so, we have to think a lot about how we're going to continue to move these models forward. And that gets back to the first topic that we talked about, which the reason they call this the third scaling law is because the way we're going to continue to scale the performance of these and get to that 3 or 4 or 5 nines of performance on a task for agents and models and all the things around them that haven't been invented yet, is going to be with inference time compute algorithms.
Yeah, and you mentioned this space is really about a year old and developing. So this is very bleeding edge. Zooming out a bit, one thing that I'm very passionate about is decentralization, open models. I really believe the future of super intelligent AI is too important to leave just up to big tech. And so something that we're seeing in the research is the importance of inference time compute in the open source world.
Yeah, I mean, that's the area that, if you want to use Llama or Quinn or one of these open source models, they're quite far behind the main frontier model labs, right? Particularly Anthropic and OpenAI in terms of their performance. And so when if you're an enterprise or you're a government or you're some kind of group that for whatever reason wants to run your own infrastructure, wants to really control your own data and all the things that go around with that for privacy reasons or competitive reasons or whatever it may be, you run into this problem where you're faced with either relying on Anthropic and OpenAI or someone like that, and risking whatever concerns you have, about your data exposure, or you have to accept some open source models, and they currently are sort of pretty far behind on these reasoning capabilities. And so it's part of what sparked the idea for Neurometric, which is this idea that we could be a layer on top of that initially for the open source models, so that you don't have to build your own chain of thought pipeline over and over again and stuff. But these things come out of the box. You can build, test, deploy, benchmark against lots of things. Now, it turns out we did not expect this would have a big impact on OpenAI's models, for example, but it actually turns out it does as well. So, sort of plugging in anything into the platform, I think works for that. But I've seen some really good data in the last year that open source is going to win. And look, I don't think that's going to hurt the foundation model labs at all. I think we're talking about AI inference is probably going to be one of the biggest markets of all time, right? Up there with real estate and things like that. I mean, it's going to be a core part of the world, many trillions of dollars. And so there's going to be a lot of really big, really valuable companies built in this space. And even though I suspect open source will take sort of a third to half of, the sort of model business long term, you're still going to have multiple massive winners on the closed model side, I think.
Absolutely. So where are we at today? Who's the first user?
Well, I think there's two types of people that really like to adopt new products and new ideas. And, the first is when I did my first company, and it was the first time we sold to IT departments, one of the things we learned is IT departments do not buy according to demographic buckets. So a lot of products you sell into companies based on demographics, where they're located, how large they are size-wise, and various things like that. IT groups tend to buy according to a psychographic, right? So it's how do they think about IT? Do they think about IT as a cutting edge thing that gives them an advantage against other people? Do they think about it as they want to be best of breed? So let somebody else adopt the cutting edge thing, but once it starts to get some traction, we'll adopt it. Do they think it's risky and they only want to go to mainstream stuff that's widely adopted? Or do they just think it's a cost center and they just want the cheapest stuff that they can find? And those categories tend to cut across size and industry and geo. So one of the things that I learned is there's just a psychographic here of people that if you start to go out and say, you can do this new thing with inference time compute, they're the kind of people that'll just take to it and go, well, that sounds cool. I want to play around. It's a personality trait. It's a psychographic. And then this, the second group, I think, and the people that we've seen most interested in this concept are, those kind of hacker types, right? The people that program all day and then go home on the weekend and program and contribute to open source and write a lot of code, and they think it's fun and interesting. And those people are always just. I think we're these people, which is why we, have started a bunch of companies between the founding team here and everything else. I think it's a lot of those people. So we're probably still a couple years away from this really being mainstream and sort of everybody having reasoning algorithms deployed, at scale in production systems. But we're seeing more and more of it, particularly as people try to build agents, because if you really want to make your agent performance, getting back to the 3 nines problem, right? You really have to think about this stuff.
Absolutely. And it's quickly emerging. There's new papers every week. And so you've been tracking some really interesting use cases and research in lesser known domains like audio, visual tasks, edge robotics. What's emerging there?
For me personally, I think the most interesting thing to watch on inference time compute is going to be what happens at the edge, because you got a bunch of moving variables there, right? At least on the data center side, it's relatively stable, right? You have NVIDIA and AMD providing GPUs. Some people still run some of the stuff on CPUs. You have a couple of big chips in Cerebras, Grok, Samba Nova that, have a little bit of market share and not much else. And I guess I should say, Amazon, Google has TPUs and Amazon has their Trainium chips and Inferentia and stuff like that. But anyway, I think on the edge, you're going to see. But the edge use cases have been slower to develop on the AI side in general. But they're going to happen, right? It's probably going to be bigger than cloud at some point, because every device we use in, automotive and phone and cameras and everything else is going to have, its own microcontrollers with AI built in. And it makes sense that you're going to want to run inference time compute algorithms on those. But you're going to probably see, you have to make a lot of different trade-offs when you design hardware for the edge, because you have a lot of times different power and physical footprint constraints and other things like that you don't have necessarily to the same extent in a data center or a big workstation. So running inference time compute on the edge, running anything on the edge is going to be a little more challenging. That market's going to be a little more fragmented in the options you have available to you. So it's going to be really interesting to see how it develops, because it's still such a largely unexplored space. There's so many things we don't know about what other algorithms are out there, what combinations of these algorithms are going to matter, how they interact with certain types of data, how they interact with certain types of models. There's a whole interesting debate going on in the academic community about exploring what they call token space versus latent space, right? So tokens are, the inputs and outputs that you use to communicate, that they're broken up, that you communicate with the model. And then the latent space is what happens internally with the models. Kind of like, the way to think about it would be like it's sort of like pseudo models of the world and what it's doing. And for some of these algorithms like chain of thought, you can run it in token space or latent space. There's advantages to both and disadvantages to both. And so there's just like some really weird, interesting things going on in this space. But yeah, I'm probably most excited about watching what happens on the edge. But I think that's still going to be a couple years to develop.
Yeah, and there's so much we can impact. There's so much to talk about. But this is the pilot episode. So we'll leave that up to future conversations. But what can people expect from Inference Time Tactics, and why should they subscribe?
Well, we're going to try to walk a line here between exploring some of the new ideas in the space, having some of the researchers on, having some of the people that are pushing the limits on, and talking about the applications, but also not make it so technical that you have to understand, matrix algebra or differential calculus to listen into the podcast. Sometimes I read some of these papers and they're just jammed with a lot of math equations that, even I, having a lot of math experience, have to work through really slowly. And that's not fun. Nobody wants to do that. So we're not going to make it super technical. And then I think we'll complement that with some some simpler episodes that also cover, kind of like beginner. Hey, here's some things to think about. Like, it might make sense at some point to do an episode on beam search and how you use it and what it means, because I think the thing that's so interesting about AI as a technology is that it's not one thing like a lot of technologies are. And it's a collection of algorithms and tactics and technologies that have kind of all been lumped together under the guise of making things smarter. And so even the people that are deep in the AI space, there's other parts of the AI space they don't understand it. I mean, everything we talk about here is mostly about LLMs, almost all going to be about transformers and neural networks, but there's there's state space machines, which are not transformers. There's whole non-neural network categories of AI, like evolutionary algorithms and Bayesian reasoning and other probabilistic forms of reasoning. There's symbolic logic processing, and so AI is this very, very broad field. So I think it'll make sense to come back sometimes and also do a series of intro lessons about what these things mean. Because, if you're a product manager or if you're kind of like partially technical person, like a lot of people that work in tech are, you want to know conceptually how something works so that you understand the limits and the boundaries of it. And, but you don't need to know the mathematical equations that guide it or anything like that. And so I think that's kind of the level that we'll try to keep this at, is sort of the intelligent technical layman, I guess we'll say.
Perfect. So let's leave it there for today. Thanks for listening. And if you're experimenting with Inference Time Tactics, we want to hear from you. Like, subscribe, share, find us at Neurometric AI. Thanks for listening.